Welcome to the fourth lab in our series on error detection and correction. In this lab, we'll focus on CRCs as a channel coding technique and show you how to calculate CRCs. The CRC, or cyclic redundancy check, is the next step in our evolution of channel coding algorithms, where we started with parity, the addition of bits, in order to add redundancy to be able to check for errors. Next came checksums, where we added bytes to check, redundant bytes to check for errors. Now we add CRCs, which are basically fancy calculations on multiple bytes. CRCs uses an algorithm to produce a checksum-like number, usually called a checksum, but it's not a sum. It's actually the result of polynomial division, which we'll see shortly. A CRC, or cyclic redundancy check, is guaranteed to detect at least one bit error in a message, and possibly more, depending on the order or level of sophistication of the CRC function. The way that a CRC is computed is it takes the data portion, or the data to be transmitted, and considers it to be the coefficients of a polynomial of degree n-1. This becomes the numerator polynomial, which is divided by another predetermined polynomial, and the polynomial is determined by the CRC function, so we could have different types of CRC functions, and we'll have different denominator polynomials. The CRC is the remainder of the polynomial division between the numerator polynomial, which is generated by the data to be transmitted, and a predetermined denominator polynomial. The remainder is the CRC. So these denominator polynomials are generally chosen to be ones that generate a lot of remainders. Let's take a look at an example on the next slide. In this example, we're going to compute the CRC for a given message. Now, the message is 10011010. The ones become the coefficients of a polynomial. There are 8 bits in this message, so n-1, so 8 minus 1, produces a 7th order polynomial. So we have x to the 7 plus x to the 4 plus x to the 3 plus x. Okay, and the x to the 6, x to the 5, x to the 2, and x to the 0 terms are where the zeros are in the message. Then we choose a denominator polynomial. For example, let's say we choose the 3rd order polynomial, x to the 3 plus x to the 2 plus x to the 0. This is equivalent to a 1, 1, 0, 1. The result of the polynomial, or the binary polynomial division, and the details will be shown on the next slide, is x squared plus 1, which is equivalent to a CRC of 1, 0, 1. So, when we send the message that we want to send, shown in blue here, we also send a CRC of 1, 0, 1, which the other side should be able to compute and compare. And if the CRCs are the same, then the message, none of the bits have been changed. Now, why would we choose a polynomial of a certain degree as the denominator polynomial? Well, the higher the degree of the denominator polynomial, the more errors we can detect in the message. Let's see an example of how a CRC can be generated by bitwise polynomial division. Let's use the message from the previous example on the previous slide. M is 1 0 0 1 1 0 1 0. And let's choose a simple divisor polynomial of x squared plus 1. This is the same thing as 1 0 1. So, how do we compute the bitwise polynomial division? Well, we start off with the message and we append 3 CRC bits because the polynomial divisor has 3 bits. So we have the message followed by the CRC bits, and then we place the polynomial divisor, the bits for that, for the divisor, directly underneath the first one in the message. Okay, so the first one in the message is the one, is 1, okay? It is the one to the leftmost of the message. So we place the divisor polynomial directly beneath. And we compute the exclusive OR on the bits. So if you remember, exclusive OR is different from OR in that 1 XOR 1 equals 0. Everything else is the same. 0 XOR 1 is 1. 1 XOR 0 is 1. 0 XOR 0 is 0, just like OR. But the only difference is that 1 XOR 1 is 0. Okay, so let's start at the leftmost column and compute the result. So 1 XOR 1 is 0. That's the first 0 that we see at the leftmost of the result. 0 XOR 0 is 0, and we compute bitwise. On the next line, we shift our divisor polynomial to the next, the leftmost one in that remainder. And we compute the exclusive OR operation on that line. We then take the divisor for the next line, 1 0 1, and we align it with the leftmost one in the remainder. And we continue this operation until the dividend goes to 0 and we're left with a remainder. Okay, the remainder in this case is 1 1 0, and that's the remainder of the polynomial division. So the CRC in this case, okay, for 101, okay, for the divisor 101 is 1 1 0. So what we'll transmit is 1 0 0 1 1 0 1 0 and then 1 1 0. As you can see, the divisor polynomial is what determines the type of CRC that's being computed. And the divisor polynomials are chosen in such a way to produce remainders, because it's the remainder that is the CRC. So there are different types of CRCs that you can produce: CRC 7, CRC 12, CRC 32, CRC 16. There are a number of popular ones used in telecommunications applications. The more complex the divisor polynomial is, the more errors that it's able to detect. So if you want to be able to detect, let's say, 2-bit errors, well then your divisor polynomial will need at least 2 terms. Okay, the more terms you have, the more bit errors you'll be able to detect. Now, one thing about CRCs is that they can't do any error correction. They can only be used for detection. However, the math, the computation, okay, especially in a telecom application, is very quick and easy and efficient to compute using hardware. Okay, and that's why it's used. It's used for very efficient detection of errors, and it's mainly used for detecting common errors that may be caused by noise in the channel. Okay, again, they're not used for detecting if somebody's trying to change specific data, because CRCs can be recomputed and the data can be manipulated to produce the same CRC. Okay, so it's not meant for security purposes, but it is used for correcting for noise induced by or errors induced by noise. Before you begin this lab, please review the following C concepts from first year. So, type def, const and its meaning, conditional compilation, and preprocessor macros. In previous labs, we've been given a main and we were asked to write the functions. In this lab, we reverse. We're going to do the opposite of that. What you're going to be given is you're going to be given functions for computing CRCs, okay? And you're going to write, or we're going to write, the main for this. Now we have CRC.cpp and CRC.h. They're written by Michael Barr and they've been placed in the public domain. They've been uploaded to eConestoga for you to download. And the functions that we're going to use come from CRC.c and CRC.h, and they are the function that we're looking at is CRC slow. Okay, it's already been written. We're just going to use it to compute CRCs. Okay, the way that it works is that message is your buffer. Okay, so it's an unsigned car. Okay, and it's basically a pointer here, because what could have been used here is unsigned car star message, and that would be equivalent to what's written there. And bytes is the number of bytes in each element. Okay, so this is how many bytes you're putting that are in message. Okay, and the function returns the computed CRC value. The data type CRC is defined in CRC.h. When we compute the CRC, please use the 16-bit version of the CRC. Our job, once again, is to write a main that tests the CRC, this function, on a buffer. We're going to put a message inside. It could be a string. Appends the computed CRC to the buffer, okay, and gets it ready for transmission, and then randomly changes some bits in the buffer and shows the effect of these changes on the computed CRC. Okay. As always, you can't change main in any way. Okay, let's get started on programming this lab. Okay, the first thing we need to do is open up Visual Studio, create a new project, and console application. Call it Lab 4. Put it on the desktop as Lab 4. Okay, and create. Okay, like we did before, we don't need this one, so let's remove and delete. Okay, what we need to do is we need to go on eConestoga and download CRC.cpp or CRC.c and CRC.h. Okay, these are going to be .c and .h. Okay, so we need to go in here. We need to copy or download them and paste them in here. So I'm going to grab them, say copy, and from download and paste them into our project folder. Okay, and then what we want to do is we want to bring them into the project. So we're going to say, so add existing item. Okay, we're going to add crc.c, and the header file we're going to add crc.h. Okay. All right, crc.h. Okay, this is where you're going to look through this this file, but this was written again by Michael Barr. Okay, and in here are a number of type defs. So type def unsigned short is CRC. Okay, so anytime we see CRC, it's basically an unsigned short. Okay, all right. So here's a defined CRC name, CRC 16. There's a number of. This is the polynomial divisor for CRC 16. This one is. So if CRC 16 is defined, and in our case, we are using. This has already been done. I've already done this for you. We've defined CRC 16 in order to use CRC 16. So we're using this guy right here, this definition. Okay. So this is the polynomial for a 16-bit CRC. This is its name. The remainder, because it's going to start off with 4 hex bits, so 16 bits. 4 hex values is 16 bits. Final value, it's 0. It's just the starting point. They have some reflections that they do, etc. But we don't have to worry about those details. Okay. The one we're looking for is CRC slow. Okay, so this one has been pre-written. Its definition is in CRC.C. Again, our job is not to redo CRC slow. Okay, we want to understand it's going to return a CRC, okay, which is unsigned short, but we're not going to have to concern ourselves with the actual implementation. What we care about is the inputs and the outputs. Okay, so what our job is going to be is to produce a lab. So we need a new item. Okay, it's a CPP, and this one's going to be main for lab 4. Okay, say add, and here we can put our usual header, right? Okay, let's do maybe one more. Okay, so this is main lab 4. This is the client, right? Oops, client for CRC, or actually we should do it this way: CRC slow. Okay, and the other one is the CRC.h is the interface, CRC.c is the implementation. Okay, and here we could put by Michael, etc. Right? You can put your name and explain what it does, but basically it's the client. Okay, I guess I don't need that much space. Okay, so first thing we want to do is, okay, this is a we could have made it a .c if we wanted to. I made it a .cpp. You know what I'm going to do? Let's change this. Let's just copy this. Control. Actually, no. Let me see if I can rename it and change the extension. Okay. Let's make it .c. Okay, good. Control S. A reason I want to make it .c is because these files are .c already. So I want to make sure that everything is exactly the same. Okay. So in this we're making the main. So int main. Okay, there's no command line arguments, so I don't really need to put anything here. I could if I wanted to. Return 0. Usually that's what we do at the beginning, just to make sure main returns something. Control S. Okay, what do we need? We need a message to compute the CRC on. Okay, so let's just put something here, a header with the variables. Okay, so we have car message. I could do car star message if I wanted to. Okay, I could do this. Okay, but what I want to do actually, no, then I would have to, actually if I just do this, look, if I do this, then it's already initialized, right? So this is going to be a constant character. So that's why CRC takes in a constant car. Let me go here, show you. So if we go to here, you see, unsigned car, it's a constant. So this is a message that is a constant. So this is actually a constant here. So we're going to put in 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say. That's going to be our message. Okay. Message buffer that we're going to look at. Okay. And now we got to see CRC.C, CRC.H. It looks like this, right? So this is what we're going to pass. This is going to be called, right? So I might as well grab it. At some point, it's going to be called. Okay. I don't need this. I do need this. I do need to supply it with a message. Okay. Now, let's see here. And bytes, I'm going to make this. I don't need this. Okay. And it's going to be, what I can do is go strlen, right? Message. Okay. So this is going to be the length. Oh, I forgot. I have to pass it just that. Control S. Okay. The name is, it's a pointer to where the message starts. Okay. So that's what it's looking for. All right. CRC.C is looking for, this is a pointer. This is like unsigned car const star and then message without this. It's the same idea. Okay. Or it's equivalent basically. All right. So CRC, this computes CRC slow, but it's got to be stored somewhere. So let's get a CRC. So we're going to go here, CRC, and this is going to be the computed CRC, let's say. Okay. And that's what this is going to be. So we're going to say comp CRC equals, okay, and we forgot something, right? We forgot to include, see how it doesn't know what this data type is because we didn't include, right? Go here, include, right? CRC.H. We need that. That's a very important part of it. Okay. Right. We're good with that. Okay. Now, the other thing we need to do, actually what I want to do, instead of using this, Control X, let's make it a data. Let's make it a data type. Let's say we are int m bytes equals strlen message. Now, Control S. Now, the problem with this, okay, wait a minute. Let's say m bytes. Now, I don't think I have string included here, so it's going to give me an error, right? So let's go in here, say include, oops, include string.h, because we need the string functions. Okay, so that's needed. Okay, so now I have m bytes is here. Okay, now what? Now what do we need? We need to be able to compute. So we compute it here. Okay, so this is going to be our computation. Compute the CRC over here, Control S. All right, and message and bytes, and let's print it somewhere. Where can we print it? Let's just go here, say print F, and then we'll test things, right? The computed CRC, let's say CRC slow is, right? And then percent. Now, it's an integer. Do I want to convert it to a string? Let's leave it as an int. Actually, wonder if we want to make it. I think we want to use the hex values because that's going to give us the best. Yeah, let's do that. And then we'll say comp CRC. Okay. Control. Oh, let me put everything on a new line. So \n and then \n. Okay. All right, let's see what happens. Let's see if it gives us. So we're using the function. We're using it as. Okay, build error. Let's find out. This is great. We're gonna figure out where the issue is. So let's see. It says here, main lab 4, error link unresolved external symbol printf reference and function. I forgot something. What did I forget? I forgot header. right? I got string, but I haven't included the other ones. So include, let's just put in the main ones. We need standard IO .h, right? We're probably going to need stuff from the standard library, so these are sort of include, right? And then that's about it. I think that's good enough. We're probably going to need these for sure. Okay, Control S, and you can either press F5 or go here. Okay. Okay, build error. Oh, problem is my BitDefender. Give me 1 sec. Let me turn off the because it's probably in a location that on my desktop that it's not going to let me do it. Give me 1 sec. Okay, so the issue for me, it's kind of new this year. I have a BitDefender. I've had it for a while, and for some reason it detects my executable for Lab 4 as a virus. So what I've done is I've just gone temporarily and I went to manage exceptions here and I just added an exception for that path. Okay, so that's what I've done for now. I will have to take it out after, but basically that's what was happening. It was being blocked. It wasn't compiling because the executable was not being produced. Okay, anyway, let's continue on. Okay, so we've tested the function. Let's see here. I'll run it just to show you. The computed CRC slow is BB3D, and this is the hex value that results from this number 1, 2, 3, 4, 5, 6, 7, 8, 9, and everybody's going to have this for their functions. Okay, you're going to have this if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and you use CRC 16. You're going to get BB3D. This is 16 bits. 4 bits for every hex number. Okay, so here's our message. We can compute the CRC. What's the next step? Well, the next step is to take our CRC, our number, okay, this value, and actually transmit it. Okay, so take this string. This thing that we computed here is a 16-bit number. We need to convert it into a string. Okay, so how do we do that? Well, there are functions in string.h here that allow us to take a number and put it into a string. Okay, so what we're going to do is we're going to use this function. I'll tell you right now. It's called sprint or sprint f underscore s. Okay, and what it is, it's going to do is going to we're going to we need something to store. So what it does, it tells you right here. Actually, it says this is your string buffer. Okay, this is the size, the length, and this is the original number. Okay, so what are we going to do? Or the format, and then there's the next. It doesn't show you here, but we'll continue it on. So what we need, so sprintf, it takes a string, okay, a string that you're going to write to. So we need that. So let's call this one it's buffer, but we're going to call it. Let's go into our variables and say we need car. Okay, the computed CRC as a string, and we need 5 elements for that string. So this is the string version of the CRC. Okay, the computed CRC, because we need to write this computed CRC into a string because we're going to append it with the message, right? So what we're going to do is we need to take, okay, we're going to write to this guy. So we're going to write to comp CRC string. Okay, then this guy says how many const size t. This is how big is your buffer? Well, it's 5. Okay, so we're going to put 5. What comes next? So we have const char star const format. So this is a format. So we're going to write in as a let's see, %x, which is hex. Okay, we're going to write it as a hex, and then we're going to write. So what are we looking for here? Is the next number is basically the comp CRC. Oops, comp CRC. Okay, and that's it. So this will write. We're going to write to this string, comp CRC string. There's a p missing. Okay, Control S to save. So basically, we're going to take the computed CRC, okay, which is a CRC value. It's an unsigned int, okay, or unsigned short, and we're going to write it to this string so that we can concatenate the strings later. Okay, great. Now what are we going to do? Now what we need to do is we need to append it to the message. Okay, so we have sprintf converts this guy to a string. What else we got to do? So this is the computed CRC. We already tested it. Actually, what we could do is go %s, right? And then we could say, oops, I should have just said comp CRC as a string, right? And then Control S, and that's it. That's all we need to do there. So save and play. And so we got the same thing, BB3D. Okay, so that's good. That means we got the conversion was done correctly. So now what do we need to do? Now we need to, okay, we're going to send a message. So the message is going to have the CRC as well. So let's say what we need is we need a new message. We're going to create a new message, right? So let's say int new message, and we'll say size. What's the new size going to be? It's going to be m bytes. Okay, so it's going to be however long this guy is, plus, okay, we have, okay, there's going to be, we have 4, okay, look, what do we have? We have 5 from here, okay, BB3D plus the string termination character was 5, right? Okay, so we have 5, okay, plus we're gonna have 0x and then a space. So we're gonna have, oh, actually we'll put a space, and we'll put 0x after the string. So we need 3 characters for the 0x because that's gonna be the CRC. Okay, so that's good, right? We have 5, so m bytes. 5 gives us the string termination character, so 4, and then this 3 is for just the 0x value here. Okay, so then what do? We need to reserve some space, right? So let's do this. So we're going to have a new, the pointer to a character. We're going to reserve some space, so new message. So this is going to contain the original message plus the CRC, right? So we have to car star, we need to cast whenever we malloc, so we need to malloc some space, and it's new message size. So this is how much space we need, right? Oh, because it's malloc, it's times, not comma, and then size of, and these are cars. They're all going to be characters. Okay, so what have we done? We're using malloc. Anytime you use malloc, you have to cast. Okay, so this we're allocating space in memory of this many this much times this size. So car is 1 byte each, so it's this many bytes. Okay, so we have this many bytes. We have this is a pointer to a character array. This guy is going to be the starting point, and we're going to write everything to this. So this new message is what we're going to send. Okay, so what are we going to do? We're going to go in, and we're going to start copying to new message. Now, how do we copy to new message? Well, you've learned this probably in previous years, is strcpy. And I'm using the safe ones here. So strcpy .s. We're starting to new message, okay? And then we're gonna copy new message size bytes, and then we're going to copy message over, okay, the original message. Okay, so this gets written up to new message size. We don't really need all that. We're going to just use message size or n bytes, but we'll just copy everything. And then what we're going to do, because this is gonna put the string termination character anyway, so we can use up to new message size. Okay, then we need to concatenate the rest of the message. So this is the original message copied to new message. Now we're going to concatenate, so we're going to use strcat_s Okay, and we're going to write to new message, starting at new message. New message. Okay, so this basically starts. Strcat is going to concatenate at the end, where the string termination character was written up here by strcopy. Okay, that's basically the byte after 9 is going to get written. So it's going to start writing there. We're going to write up to new message size. Okay, we could just say 3 if we wanted to, but I'm just going to put that here. And then we're going to put a space, an X, or sorry, a 0, then an X. So this is going to be the string, the CRC, right? So we're concatenating this, and then we're going to concat strcat underscore s. Okay, we're going to write to the end of new message. Okay, see this guy right here, this guy is going to have a string termination character as well. Okay, and we're going to, okay, we can write up to new message size if we like. And then we're going to copy our string, the computed CRC as in string form. Okay, copy that in, and then we can print the computed CRC slow is now what we're going to do. Actually, no, we're going to say, let's see, we're going to see the complete transmission is, and then we're going to write %s, but this time we're going to put new message. Okay, so new message. Okay, and the one thing that we want to do, I think this is okay. Okay, so Control S to save all. We have our return 0. So this all makes sense, I hope. All right, Control S. Let's save and see if there's any errors. Any errors? Okay, so the complete transmission is, okay, the original message, a space, 0x, because it's a hex. This is a hex number, so I just want to be clear. BB3D. All right, that's great. So we did that part. The other part of this is, the other thing we need to do here is we need to zap some bits. Okay, we need to change something in the message. Okay, we want to change something in this original message and change one of the values. So what I'm going to do, you know what? One at a time, I'm going to change one of these bits one at a time. Okay, so I'm going to make a loop. Okay, so what I'm going to do is let's say compute CRCs after, let's say zapping the characters. How's that? Something like this. Okay, and so what I'm going to do is I'm going to make a for loop. I equals 0. I realize I haven't I haven't declared I, so I'll say int I. It's going to be my for loop counter. Okay. For I is 0, I is less than, and here is going to be m bytes, right? M bytes, I plus plus. Open up, and actually it's going to be, what I should do, actually I'll just do this. I'll do this, and then do that, and then take this guy, Control X, paste it all in here. Alright, so what I need to do actually, so the first time I do it, I'm not going to zap any of the bits. Okay, I should say less than or equal to, because I want to do it 10 times basically. Okay, because I want the first one for it to be 0. Okay, and so no changes, and then so zap none of the bits, change none of the bits to a 0 in the message. Then the next time I'm going to change the first bit to a 0. The next time I'll change the after that next loop I change the second one. The next loop I'll change the third one, etc. So what I'm going to do is I'm going to say message at I equals 0. So I'm changing these numbers, well they're strings, but each one, our character, to a 0 at every loop. Okay? And that's it. That's basically what I want to do. I want to be able to see the change to the CRC as I go through these loops. All right, let's see what happens. Do I have it all in a new line? Good, I do. Okay, let's go through this and just see. Do I need an extra space after it? I guess I don't need this space. Okay, so let's go in here and make these changes. Okay, let me do it again without the space, so I don't have to open it up here. All right, so go here and good. All right, so the first one, BB3D. The second one, I make the 1 into a 0, and you see how the CRC changes to B30. The next loop, I make the second bit a 0, and you see how the bits are changing. Okay, so try it out. See if you can get the same thing. It should, the first one for sure, if everything's right, the CRC of the numbers 1 to 9 is BB3D. Okay, and that's confirmed to be correct. Okay, so that's basically it for this lab. We're using this function, the CRC slow, that someone else wrote. Okay, we're looking at the interface. Okay, and we're using the interface. Okay, imagine we don't even have the implementation. Okay, sometimes it's compiled and you can't see how it's implemented. Okay, so we sort of ignored it, and we used the interface, the .h file, to see everything. Okay, the inputs and outputs. And there's a little bit of a string manipulation here. I showed you strcpy, strcat. If you want, this may not run in a Linux environment. You might have to take out the _s when you convert it over to if you want to run this in Linux or Ubuntu. And I've showed you how to do that already in the very first lab. So please try that out and see that you can get this lab to work also in Linux. All right, that's it for today. Thanks for listening. Thanks for watching, and I hope you enjoyed the lab.